Hi, Stu Schwartz, MasterMathMentor.com. This is video AB19b. The topic is function analysis, and it covers the AB manual, pages 112 through 116. When we examine functions with curves, we will define their curvature in terms of concavity. Concavity comes in two flavors, concave up and concave down. This curve is concave up. We say it holds water, as water poured into it will collect and hold. This curve is concave down. We say it spills water, as water poured onto it will spill down. On both curves, draw tangent lines at the points shown. The tangent lines are now shown. Can you determine a relationship between the slopes of the tangent lines on the concave up curve as we go left to right, as well as a relationship between the slopes of the tangent lines on the concave down curve as we go left to right? I show some possible slopes on the concave up curve. Notice how the slopes are increasing in value. They start at -4 to -3, get to 0, and then continue with it. Slope is 1, slope is 2, etc. So on the concave up curve, the slope, which we know is the derivative, is increasing. Notice how the reverse is true on the concave down curve. The slopes are decreasing. They start at 4, then 3, get to 0, and then continue -1 down to -4. So the slope, which we know is f prime of x, is decreasing on concave down curves. I'll say this important concept slowly, and if you have to, stop the video and listen to it again. The instantaneous change in a quantity is its derivative. So f prime of x increasing means that the change in f prime of x is positive. But the change in f prime of x is f double prime of x. So f prime of x increasing means that f double prime of x is greater than 0. Using the same logic, f prime of x decreasing means the change in f prime of x is negative. The change in f prime of x is f double prime of x. So f prime of x decreasing means that f double prime of x is less than 0. So just as the derivative f prime of x was tied into whether a function is increasing or decreasing, f double prime of x is tied into whether a function is concave up or concave down. So if f double prime of x is greater than 0 for all x in an interval, the graph is concave up on that interval. If f double prime of x is less than 0 for all x in that interval, then the graph is concave down on that interval. And if f double prime of x equals 0 for all x in an interval, the graph has no concavity on that interval, which means that it graphs a line. We define the term inflection point. This is the point on the curve where f changes its concavity, meaning it switches from concave up to concave down, holding water to spilling water, or from concave down to concave up, spilling water to holding water. So on the blue increasing curve, We see that first the graph is concave down because f double prime of x is less than 0, and it switches to concave up because f double prime of x is greater than 0. That point where it switches is the inflection point. The same is true on the curve that is decreasing. The curve starts concave up as f double prime of x is greater than 0, and switches to concave down because f double prime of x is less than 0. That point where it switches is called the inflection point. On these two curves, since f prime of x is equal to 0 at these inflection points, we call these stationary inflection points. We will see in our examples that not all inflection points are stationary. There are many real-life examples of inflection points. When COVID-19 started to spread in China, it went up slowly and then its growth increased. That meant that dy dt, where y is the number of cases, was positive, and the second derivative of y was also positive as the case curve was concave up. Later, dy dt was still positive, but the second derivative of y was clearly negative. Somewhere around February 17th was the inflection point, where the number of cases was increasing, but not as fast. This happened in many U.S. states as well, and people became less careful, and another inflection point was reached, and the curve became concave up again. The headline should really read, "The growth of new cases in China has slowed." This is really saying that the growth of new cases, dy dt, is negative, or the second derivative of y with respect to t is less than 0. On a happier note, when you ski down a mountain, the slope changes continuously. The path you travel increases the slope, and then it is less steep, then more steep, then less steep. So your path down the mountain will have numerous inflection points. On the picture, every one of the green marks on the path represents an inflection point. Another time where we use inflection points is in straight line motion. Let's review a bit. In straight line motion, we had three functions. First, s of t, the position function that determined where on a straight line you were based upon time. V of t, which was the derivative of the position function, was called the velocity function. It talked about how fast you were traveling and in what direction you were traveling. We also had a of t, which was the derivative of the velocity function and the second derivative of the position function. It referred to acceleration. It referred to how fast the velocity was changing. You are in your car, stopped at a red light. You see the light in the next block is red. Your light turns green, and you start off accelerating. Your hope is that the next light will turn green, but it doesn't. At some point between the two lights, you must make the decision to stop accelerating and begin braking. From a calculus point of view, that is where v prime of t goes from positive to negative. And since v prime of t is the same as a of t, which is the same as s double prime of t, that point of decision is the inflection point. That decision does not have to be halfway between the lights. If you delay in making the decision, hoping the light will turn, then you are in for a very hard stop. On problems 9 and 10, you are asked to determine intervals where f of x is concave up, concave down, and the location of any inflection points, and also to confirm your answers graphically. Number 9 reads f of x equals x cubed minus 3x squared plus 3. The best way to find concavity and any points of inflection is to find the second derivative. So we get f prime of x equals 3x squared minus 6x, and f double prime of x equals 6x minus 6. We set that equal to 0, and we get x is equal to 1. We now make a sine chart for f double prime of x with two intervals, to the left of 1 and to the right of 1. To the left of 1, we get negative, and to the right of 1, we get positive. That tells us that f is concave down on the interval negative infinity to 1 and concave up on the interval 1 to infinity. That means that x equals 1 is an inflection point. The graph confirms our answer. Notice that at x is equal to 1, we do not have a stationary inflection point, as it's clear that the first derivative is not 0 there. 10 reads f of x equals 8x cubed minus 2x to the fourth plus 3. We take our first derivative and get 24x squared minus 8x cubed. Our second derivative is 48x minus 24x squared. We can factor out a 24x times the quantity 2 minus x, set that equal to 0, and we get x is equal to 0 and x is equal to 2. We use those for our sine chart, and we find that our sine chart alternates, going from negative to positive to negative. Therefore, our curve is concave down on the interval negative infinity to 0 and 2 to infinity. It's concave up on 0 to 2. Finally, there are inflection points at x is equal to 0 and x is equal to 2. The graph confirms our answer. Notice that at x is equal to 2, we do not have a stationary inflection point because the first derivative at that point is clearly not 0. But at x is equal to 0, we do have a stationary inflection point because the value of f prime of 0 equals 0. Let's try a harder one. Number 11, f of x equals 4 over x squared plus 3. You may now understand why it was necessary to simplify f prime of x as much as you can, because you need to make it as easy as possible to take f double prime of x. And also, you may also now understand why factored form for both numerator and denominator are so important. We start by taking f prime of x, treating it as a quotient, and we end up with negative 8x over x squared plus 3 quantity squared. To take the second derivative, again we treat it as a quotient, squaring the denominator, and upstairs getting x squared plus 3 quantity squared times negative 8 minus negative 8x times 2 times x squared plus 3 times 2x. The best way of dealing with this algebraically is to factor out an x squared plus 3, and we get inside the brackets negative 8 times the quantity x squared plus 3 plus 32x squared. This turns out to be negative 24 times x squared minus 1 over x squared plus 3 to the fourth power. We now find critical values for both numerator and denominator. For the numerator, it's plus or minus 1. For the denominator, there's no values that make x squared plus 3 equal to 0. So our sine chart will only have two values, negative 1 and 1. Plugging in values in our interval, we get plus, then minus, then plus. So our function is concave down on negative 1 to 1, and then concave up on negative infinity to 1 and 1 to infinity. meaning that there are inflection points at x is equal to plus or minus 1. Our answer is confirmed graphically. Notice that our inflection points at x is equal to plus or minus 1 are not easily determined by I. It is very hard to pick up exactly where the inflection point is, and that's why we go through the math. Students sometimes mistakenly think that they don't have to make a Sine chart for f double prime of x. Just finding where f double prime of x equals 0 is sufficient. That is not true. If f double prime of c equals 0, that does not necessarily mean there is an inflection point at c. For instance, if f of x equals x to the 6th, f prime of x is equal to 6x to the 5th, and f double prime of x is equal to 30x to the 4th. Setting that equal to 0, we get x is equal to 0. But the sign of f double prime of x to the left of 0 and to the right of 0 is still positive. There is no inflection point at x is equal to 0. Let's review a bit. In testing for relative extrema, we had our first derivative test. It stated that we will find all critical values, c, and first determine if f prime of x changed from negative to positive at x is equal to c by making a Sine chart. Then f had a relative minimum at that point. If f prime of x changed from positive to negative at c, then f had a relative maximum at x equals c. And if f prime of x was both positive on both sides of c or both negative on both sides of c, then that point was neither a relative minimum or relative maximum. There is another test for relative extrema, which is also sometimes more useful than the first derivative test, and it is called the second derivative test. Let f be a function such that f prime of c equals 0, and the second derivative of f exists on some open interval containing c. If f double prime of c is positive, then f has a relative minimum at the point c f of c. If f double prime of c is negative, then f has a relative maximum at the point c f of c. And if f double prime of c equals 0, then the test fails, and you must use the first derivative test to ascertain relative extrema. Problems 12 through 14 ask to use the second derivative test to determine relative extrema. Number 12 reads f of x equals 6x to the 5th minus 5x to the 6th. Our first derivative is 30x to the 4th minus 30x to the 5th. We can factor out a 30x to the 4th times the quantity 1 minus x and set that equal to 0, getting our critical values as x is equal to 0 and x is equal to 1. Our second derivative is 120x to the 3rd minus 150x to the 4th. So we look at f double prime of 0 first and find that they're equal to 0, meaning the second derivative test is inconclusive. But since f prime of x doesn't switch signs at x is equal to 0, there is no extrema there. F double prime of 1 equals negative 30, and therefore there's a relative maximum at x is equal to 1. Number 13 reads f of x equals the square root of x squared plus 4. Our first derivative is x over the square root of x squared plus 4. Setting that equal to 0, we get x equals 0. The denominator cannot equal 0. So our second derivative, using the quotient rule, is square the bottom, and we get x squared plus 4. And upstairs we get the square root of x squared plus 4 minus x squared over the square root of x squared plus 4. You could plug in 0 at this point. I choose to simplify it and get, by multiplying top and bottom by the square root of x squared plus 4 over the square root of x squared plus 4, we get 4 over x squared plus 4 quantity to the 3/2. F double prime of 0 is 1/2, meaning that there is a relative minimum at x is equal to 0. Number 14 reads f of x equals sine x times cosine x on the interval negative pi over 2 to pi over 2. Our first derivative is cosine squared of x minus sine squared of x. Set that equal to 0, and that means that cosine squared of x equals sine squared of x, or tangent squared of x is equal to 1. And that happens when x is equal to plus or minus pi over 4. We then take our second derivative and get negative 4 sine x cosine of x. So the second derivative at negative pi over 4 is negative 4 times negative square root of 2 over 2 times square root of 2 over 2, and that is 2, meaning that there is a relative minimum at x equals negative pi over 4. At x equals pi over 4, f double prime of pi over 4 is negative 4 times square root of 2 over 2 times square root of 2 over 2, and that equals negative 2, meaning that there's a relative maximum at x is equal to pi over 4. So let's put it all together. First of all, if f prime of x is positive, then we look at f double prime of x. If f double prime of x is also positive, it means that f of x is increasing and concave up. If f prime of x is positive and f double prime of x is 0, it also means that f of x is increasing, but there is a possible inflection point. If f prime of x is positive and f double prime of x is negative, that means that f is increasing, but the curve is concave down. Let's focus on f prime of x being less than 0. If f double prime of x is positive, that means that f of x is decreasing, but concave up. If f prime of x is less than 0 and f double prime of x equals 0, it also means that f of x is decreasing and there is a possible inflection point. If f prime of x is less than 0 and f double prime of x is less than 0, it also means that f of x is decreasing and concave down. Let's focus on f prime of x equaling 0. If f prime of x equals 0 and f double prime of x is greater than 0, it means that we have a relative minimum and the curve is concave up. If f prime of x equals 0 and f double prime of x is less than 0, it means that we have a relative maximum and the curve is concave down. Finally, if f prime of x equals 0 and f double prime of x equals 0, we really can't make a conclusion. There could be a relative minimum, there could be a relative maximum, and there could be an inflection point. On number 15, there are 8 graphs labeled A through H, each showing a point on the curve. Identify which of the term or terms refers to that point. A critical value, a stationary point, a relative minimum, a relative maximum, an inflection point, or a stationary inflection point. In A, because the tangent line to the point is horizontal, therefore its derivative is 0, making it a critical value and also a stationary point. Since the curve increases to the left and decreases to the right, it is a relative maximum. In B, the exact same logic applies as did in A, except that since the curve decreases and then increases, the point is a relative minimum. In C, this is a critical value as the derivative equals 0, making it a stationary point as well. It is an inflection point because the curve switches from concave up to concave down, It's also a stationary inflection point because the derivative equals 0 at that point. On D, the tangent line is certainly not horizontal, so it is not a critical value. However, it does appear to be an inflection point, as it appears to be concave up to the left and concave down to the right. Inflection points are always difficult to determine by eye. In E, this is a cusp point. The tangent line is vertical, making the derivative undefined and making the point a critical value. It is a relative max as the curve is increasing to the left, decreasing to the right. It is not a point of inflection as concavity does not change. In F, this is a critical value as the derivative does not exist. This graphs a corner. However, it is a relative max because the curve increases to the left and decreases to the right. In G, the tangent line is vertical, making the point a critical value. It is an inflection point as the curve is concave down and then switching to concave up. It is not a stationary inflection point because the derivative is not equal to 0 there. H is only a critical value as the derivative does not exist there. It is not an inflection point as the curve switches from no concavity, lines have no concavity, to concave down. That is not an inflection point. It must switch from concave up to concave down or concave down to concave up to be an inflection point. Traditional calculus courses require students to graph functions given its equation. However, with the advent of graphing calculators and technology and graphing apps, there is now less emphasis on actual graphing functions and more emphasis on describing graphs in terms of increasing, decreasing, relative extrema, concavity, and inflection points. We will use that approach and not actually expend energy on the graphing, which can be entirely time-consuming. The problems we will show graphs as a conformation, but all the work will be done using calculus techniques. Number 16 reads f of x equals x to the fourth minus 4x to the third minus 18x squared plus 108x minus 2. We would like to find critical values, intervals of increasing or decreasing, relative mins and relative maxes, intervals where the function is concave up and concave down, any inflection points, vertical asymptotes, if any, and the limit of f of x as x approaches infinity or negative infinity. We start with first derivative work. Our first derivative is 4x to the third minus 12x squared minus 36x plus 108. We can factor out a 4x squared from the first two terms and a 36 from the second two terms. And we get 4x squared quantity x minus 3 minus 36 quantity x minus 3. Factor it into 4 quantity x minus 3 squared, quantity x plus 3. Set that equal to 0, and we get critical values of x is equal to plus or minus 3. Next, we do our sine chart work. Our first derivative is negative to the left of negative 3, positive between negative 3 and 3, and positive to the right of 3. So the function is increasing from negative 3 to infinity. It does level off at x is equal to 0, but increasing functions can level off. The decreasing interval is from negative infinity to negative 3, meaning that this curve has a relative minimum at x is equal to negative 3 and no relative maximum. We now do our second derivative work. F double prime is 12x squared minus 24x minus 36. factoring into 12, quantity x squared minus 2x minus 3, or 12, quantity x plus 1, x minus 3. Set equal to 0, we get x is equal to negative 1 and 3. Making a Sine chart for f double prime of x, we get 3 intervals. F double prime is positive to the left of negative 1, negative between negative 1 and 3, and positive to the right of 3. So our function is concave up between negative infinity and negative 1, and 3 to infinity, concave down between 1 and 3. So we have inflection points where the concavity changes at x is equal to negative 1 and 3. Since the function does not have a denominator with any x's in it, there are no vertical asymptotes. And since the highest power term is x to the fourth, the limit of f of x as x approaches either infinity or negative infinity is infinity. Shown is the graph that confirms our answer. We show our relative minimum at x is equal to negative 3 and our two inflection points at x is equal to negative 1 and x is equal to 3. In order to determine the actual points, we would have to plug those values into the function itself. At x is equal to negative 3, f of negative 3 is equal to negative 299. At x is equal to negative 1, f of negative 1 is equal to negative 123, and f of 3 is equal to 133. Note that the inflection point at x equals 3 is stationary, while the inflection point at x is equal to negative 1 is not. Number 17 reads f of x equals x plus 4 over x minus 4. We can choose to deal with this in the form it's in, or we could get it into a fraction form. I'll choose to keep it the way it is. Also realize that the domain is x does not equal 4. We take the first derivative and get 1 minus 4 over x minus 4 quantity squared. It is best to express the derivative as a fraction. So getting a common denominator, we have x minus 4 quantity squared minus 4 over x minus 4 quantity squared. When we set that equal to 0, we set the numerator equal to 0, and we end up with x squared minus 8x plus 12 equals 0, factoring into x minus 2 times x minus 6. And we get critical values of x is equal to 2 and 6. Realize that we also have to set the denominator equal to 0 for critical values, and notice we also get an x equals 4. So in our Sine chart for f prime, we have f prime is 0 at x is equal to 2 and x is equal to 6, but infinite at x is equal to 4. We have 4 intervals that are positive, then negative, then negative, then positive. So we conclude that our function is increasing from negative infinity to 2 and 6 to infinity. It is decreasing from 2 to 4 and also 4 to 6, meaning that there's a relative minimum at x is equal to 6 and a relative maximum at x is equal to 2. In taking our second derivative, it is far easier to work with f prime of x equals 1 minus 4 over x minus 4 quantity squared. So our second derivative is 8 over x minus 4 quantity cubed, meaning that there's only one critical value, and that's that x is equal to 4 because the numerator cannot equal 0. So the Sine chart switches from negative to positive at x is equal to 4. Meaning the curve is concave down from negative infinity to 4 and concave up from 4 to infinity. Note though that there is no inflection point at x is equal to 4 because the curve is undefined there. That's why it's very important at the beginning to get straight your domain. This curve does have a vertical asymptote, though, at x is equal to 4. Our limit of f of x as x approaches infinity is infinity, and our limit of f of x as x approaches negative infinity is negative infinity. Finally, the graph of confirmation. Notice that there are two critical values, and at x is equal to 2, the value of the function is 0. At x is equal to 6, the value of the function is 8. 18 reads f of x equals 2x minus tangent of x on the interval 0 to pi. Typically, the AP exams will have a function analysis problem involving trig. First derivative work, f prime of x equals 2 minus secant squared x, and we can write that as 2 minus 1 over cosine squared x. And again, it is a good idea to write your derivative as a fraction, 2 cosine squared of x minus 1 over cosine squared of x. We set the numerator equal to 0, 2 cosine squared of x is equal to 1, and we get critical values at pi over 4 and 3 pi over 4. We set the denominator equal to 0, and we get pi over 2. Plugging in some friendly angles to the derivative, like pi over 6 or 5 pi over 6, we see that there are 4 intervals that are positive, then negative, then negative, then positive. So the function is increasing on 0 to pi over 4 and 3 pi over 4 to pi, decreasing on pi over 4 to pi over 2, and pi over 2 to 3 pi over 4, meaning that there is a relative maximum at x is equal to pi over 4 and a relative minimum at x is equal to 3 pi over 4. For the second derivative, it is easier to use the f prime of x equals 2 minus secant squared of x, and therefore f double prime of x equals negative 2 secant x tangent of x. It is best to write the second derivative as a fraction, and putting everything in terms of sines and cosines, we get negative 2 sine of x over cosine cubed of x. The numerator is equal to 0 at 0 and pi. The denominator is equal to 0 at pi over 2. So our sine chart has two intervals, and the second derivative is negative, then positive. So our curve is concave up on pi over 2 to pi, concave down on 0 to pi over 2. There are no inflection points, as the only candidate is pi over 2, but the function is undefined there. But there is a vertical asymptote at x is equal to pi over 2. Since the function is only evaluated on 0 to pi, it makes no sense to talk about limits of f of x as x approaches infinity or negative infinity. Our graph confirms the solution. Our relative max is at pi over 4, and the corresponding y-coordinate is pi over 2 minus 1, while our relative min is at the point 3 pi over 4, and the y value is 3 pi over 2 plus 1. Later in the course, we will be looking at a number of word problems where we have to interpret sentences and create variables and equations from them. We have already done this to an extent in our study of related rates. Let L be a function representing the number of people in line for tickets. Stop the video and write the 6 sentences in terms of the variable L. If L represents the number of people in line, the line getting longer is interpreted that L is increasing, and therefore L prime is greater than 0. B reads the line is getting shorter. For the same reasoning as in A, that means that L prime is less than 0. C reads the line's length isn't changing. That means that the number of people in line for tickets is staying the same, and therefore L prime has to equal 0. Let's get a little harder. D reads that the rate of change in the line is increasing. Let's go back to A, which stated that the line is getting longer. If L prime equals 2, might mean that every minute 2 more people join the line. Then, perhaps in the next minute, 3 more people join the line. And then the next minute, 4 more people join the line, etc. That means that L prime is increasing, meaning that L double prime is positive. E reads the line is getting longer, but at a slower rate. We know from A the line getting longer is L prime greater than 0. Perhaps in the first minute, 4 people join the line. In the second minute, maybe 3 people join the line. In the third minute, 2 people join the line, etc. So the line is getting longer, but at a slower rate, meaning that L double prime is negative. F is the trickiest of them all. The line is getting shorter, but at a slower rate. We know through B the line is getting shorter means L prime is less than 0. But what does at a slower rate mean? Suppose in the first minute, 4 people leave the line. That means the length of the line is changing by -4. In the second minute, 3 people are leaving the line. That means the line is changing by -3. In the third minute, 2 people leave the line. That means the line is changing by -2. So our numbers have gone from -4 to -3 to -2, meaning that L double prime is positive. Calculus is not just doing computations. It's all about interpretation, and we will be working on these skills throughout the rest of the course. Finally, most likely in your teacher's exams, and certainly on the AP exam, you will have to explain the logic behind your answers. Watch your language. Be very careful about the use of the words positive and increasing, negative and decreasing, the increase and the rate of increase. They are not the same. F is increasing is not the same thing as F is positive. F prime is negative is not the same thing as F double prime is decreasing. A price increase of $5 this week is not the same as $5 per week. Watch your language.